Chapter 14, Inductance and RL Circuits, Questions and Experiment. This is from Section 4, Advanced Electronic Circuits. This is Chapter 14, Inductance and RL Circuits, only questions and experiments. For the full chapter, please look for that Chapter 14 video. Review questions for Section 14.1. First question is to define inductance. An inductance is the opposition to change in current by the effect of energy stored in a magnetic field. This magnetic field is stored in the coil, although temporarily. Again, the coil from the inductor, which we'll define here shortly. What is the difference between inductance and resistance? And the answer is inductance is the resistance to change in current via magnetic field, and the resistance is the opposition to change due to other factors like material, load, and other factors that deal with resistance. Question 3, the unit for inductance is the Henry. Question 4, find the time constant in the circuit shown. For that, we use the formula T equals to L, which is inductance, divided by R, or resistance. In this case, 5 Henry divided by 100 ohms gives us 0.05, and that's 0.05 seconds. Jumping on to review questions for section 14.2, make sure you have studied the material in the chapter provided in the video for this chapter, chapter 14. Question number 1, the effect of 2 or more coils sharing the energy of one coil is called fill in the blank, and that is mutual inductance. Question 2, as coils are connected in series, their total induction increases or decreases, and the correct answer is increases. Question 3, as coils are connected in parallel, their total induction increases or decreases. In this case, the correct answer is decreases. Question 4, a 1.5 Henry and a 500 millihenry coil are connected in series. What is their total inductance in henries? In this case is 2 henries. All you have to do is more or less like resistors. You add 1.5 plus 500 millihenries, which is basically 0.5 henries. You get 2 henries. Question 5, a 3 Henry and a 6 Henry coil are connected in parallel. What is the total induction in henries? For this, we use the formula ILT equals 2, in this case 1 over L1 plus 1 over L2, which in this case we have 1 over 3, 1 divided 3 plus 1 divided 6. If we do a little bit of algebra, we find that we have to have 2 divided 6 plus 1 divided 6. We have to have the least common denominator, which is 6 in this case. So 2 divided 6 is 1/2. And 1 divided 6 is also 1/2. excuse me, we have ultimately 2 divided 6 plus 1 divided 6. So we add the two fractions, which we get 1/2, which is equal to 0.5 henries. Jumping on to review questions for section 14.3. What is reactance? And the answer is that the reactance is the opposition to change in current due to induction or capacitance. In this chapter we study reactance due to induction. Number 2, the actual opposition to change in current offered by an inductor is called inductive reactance. Question 3, find the inductive reactance in the following diagram. We have a 4.5 Henry inductor at L1, and we have a 400 Hertz AC power source. Again, we're going to find the inductive reactance XL. We use the formula, which is XL equals to 2 times pi times frequency times the inductance. In this case is 2 times pi, which is 3.14 approximately, times 400, which is the amount of hertz in the AC source, times the inductor of 4.5 henries, and we ultimately get 11,304 ohms for inductive reactance. Question 4, the actual power used by a circuit is the fill in the blank true power. Question 5, find the values in the following figure, where A is XL, B is Z or your impedance, and C is your current. For the first one, XL, your inductive reactance, again we use the formula 2 pi FL. In this case we have 2 times 3.14, which is pi, times 120 Hertz, which is our voltage frequency of AC, times your inductor size in henries, which is in this case 2.5, and we get 1884 ohms. To find Z, which is your impedance, again is your resistance to AC, total resistance to AC. And again, if we have a resistor and a inductor in a circuit, the impedance, which is your total resistance, has to be the combination of those two types of resistors, which are effectively resistors, your inductor and your resistor. And you cannot just simply add them. You need to have a formula, which is basically a kind or a variation of the Pythagorean theorem formula. And in this case we have that formula as Z equals to square root of all under the square root of R, or resistance squared, plus your inductive reactance squared. So we have in this case the square root of 2500 squared, which is your 2.5 the 2500 ohm resistor. You square that plus the 1884 inductive reactance that we just found, and that is also to be squared. When you square those two under the square root, we get 625,000, or we get 6,250,000 plus 3,549,456, and ultimately we get, when you square root their addition, you add those two and square root it, we get a impedance of 3,130, and that is measured again in ohms. The summary for the chapter, since the audio got cut off in the last recording, the recording for the chapter, we'll go over it here. Summary: inductance is the property of a circuit that opposes any change in current. An inductor is a component that produces an inductance in a circuit. Other names for an inductor are coil, reactor, and choke. The unit for inductance is the Henry, symbolized by a capital H. Some factors that affect the amount of inductance are the number of turns of coil, the diameter of coil, the core material of coil, the type of winding, spacing between the windings or the length of the coil, and the size of the wire. The time constant of a coil is the amount of time it takes for the current to rise from 0 to 63.2% of its maximum value. The formula for time constant is shown on the bottom here as T equals to inductance, or L in henries, divided by R, or resistance, in ohms. Mutual inductance is two or more coils linked by magnetic lines of flux. The following formulas are used to compute inductance in a circuit. For an inductor in series, we use the formula L total, or inductance total, equals to inductance 1 plus inductance 2 plus inductance 3, and so on. For inductors in parallel, we use the formula 1 divided by inductance total equals to 1 divided by inductance 1 plus 1 divided by inductance 2 plus 1 divided by inductance 3, etc. A shortcut when only two inductors are in parallel is the following, where inductance total equals to inductance 1 times inductance 2 divided by inductance 1 plus inductance 2. Inductive reactance, or XL, is the amount of opposition offered to a change in current by an inductor. It is measured in ohms. The formula for inductive reactance is XL equals to 2 times pi times frequency times inductance. Again, inductance is measured in henries. Again, where pi equals 3.14, F equals frequency in hertz, and L, inductance, equals to henries. Reactive power is power reflected back to the source. It is measured in VAR. True power is power actually used in a circuit. It is measured in watts. Apparent power is the combination of reactive power and true power. It is measured in VAs. Power factor is the relationship between true power and apparent power. The total opposition to a change in current in an inductive and resistive circuit, RL circuit, is the impedance, Z. It is measured in ohms. Impedance can be calculated using a graph of the resistance and a reactance vector, using the Pythagorean theorem, or using the phase angle and trigonometry. Finally, when a resistor and a conductor are in parallel, the branch voltages are the same. However, the branch currents will be 90 degrees out of phase with each other. And now test your knowledge questions. First question is to draw a graph showing the rise and decay of current in an RL or resistive inductive circuit. That graph is shown on the top right of your screen. 2. What is the formula for determining the time constant? And the time constant formula is shown on the right side of your screen, where T equals to inductance divided by resistance. Again, inductance is measured in henries, resistance in ohms. Question 3, draw the symbol for an inductor with an iron core, which is shown at the bottom. Question 4, reactance is measured in, again, ohms, and reactance is symbolized as the capital letter Z. In a series, question 5, in a series circuit, we have inductance of 2 henries, we have resistance of 500 ohms, we have the power at the source of 100 volts, and it is an AC source of 60 hertz. Given those, find the following. First one, we find inductive reactance. And that is A. We follow the formula for inductive reactance. Again, XL, which is inductive reactance, equals to 2 times the equivalence of pi times frequency times inductance in henries. And plugging in our values, we have 6.28 for our multiplication between 2 and pi, times 60, which is our hertz in AC, and 2, which is our henries for the inductance. We ultimately get 753.6 for our inductive reactance. Moving on to the next step, we have to find impedance. We use the formula for impedance. We already know what our resistance is and what our inductive reactance. We plug those in. Again, we have to square those, add them up, and find out their square root, the square root of that addition. We ultimately get, in this case, impedance equals to 904.385 ohms. Moving on to step C, we have to find our currents. In this case, we use Ohm's law. Again, we have to substitute impedance with our resistance for Ohm's law, which again, impedance is the total resistance of a RL circuit. We know that. Impedance, which is 904.39. But we have to divide that. We have to make the division of 100 divided by 904.39, which we get 0.11 amps for our current. Next step, we have to find our voltage drop at the resistance or the resistor. We have to find our resistive voltage drop as opposed to our impedance, as opposed to our inductance voltage drop. We have to find our resistive voltage drop. We use Ohm's law. We simply plug in our current and our resistance, which we get 55.29. Moving on to the next set of problems, we have to find the power drop at the inductive reactance. We use the formula EXL equals to I times XL. We already know our current, we plug that in, 0.11, and our inductive reactance is 753.6. We just found that on the last set of steps. And we ultimately get power voltage drop out at our inductive reactance of 82.896. Moving on to the next step, step F. We have to find our theta, which is the angle at our phase angle. For that, we get the cosine we put our cosine equals to resistance times reactance, and using that equation we can find out our phase angle. So cosine equals to, in this case, 500 divided by 904.39, which is equals to cosine theta equals to, in this case, 0.522. Excuse me, 0.552. Get the cosine of that using your calculator. Make sure your calculator is in degrees mode. Go to your mode or your options. Make sure that your angle mode is set to degrees instead of radians or radians. And use your shift key, and then use your cosine negative to the negative first key, which should give you 0.552 in this case. Excuse me, use your cosine negative to the first power key and then punch in 0.552, which should give you 56.49 degrees if your setting is correct. So theta equals to 56.5 degrees, and that is your phase angle. Moving on to the next step, step G, find your PF. But for that, we have to find your apparent power and your true power. First, we move on to the true power, step H. We have the formula I times E times cosine theta, which is 0.11 times 100 times 0.55 in this case, which gives us 6 watts. To find your apparent power, again, current times voltage, 0.11 times 100 in this case gives us 11 volt amps, VAs. And then to find our PF, step G, we simply divide apparent power by true power, in this case 11 divided 6, or 1.8 watts. Drawing the vectors for this problem, we use just a simple graph paper, squares as our scale, 1 square per, in this case, per 100. So we have 500 going to the right on the bottom for our resistive value, and we get 753 approximately going up from that point for our inductive reactance value, 753 approximately. So we tie the 2 points, the beginning of the resistive value vector and the end point of the inductive reactance value vector. We tie it up, we get approximately 905 for our impedance. In this case, our theta is 56 degrees, as we have found out through our calculations. To move on to a quick interlude for this chapter dealing with inductance, inductive heating. An iron or steel part inside an energized coil produces a magnetism as well as heat. This heating effect is caused by hysteresis and eddy currents generated by the magnetic field. The amount of heat produced is directly related to the intensity of the magnetic field and the frequency of the applied AC, or alternating current. In normal electronic applications, this heating effect is a waste of power, and it is also undesired. The effects can be reduced by using laminated metal. Today, there are many uses for one's undesired heating effect. For the once undesired heating effect, one such product is found in a relatively new household stove top that is designed to incorporate the heating effect of induction. In this stove top, a cooking unit is designed with a coil located under the ceramic top. When a metallic or some other induction efficient cooking pot is placed on the cooking top, a magnetic field is induced by the coil hidden beneath the counter surface. The coil does not produce heat in the same manner as a conventional electric cooktop. The conventional electric cooktop uses resistance, wire, inside coils to produce heat. Instead, the magnetic field produces heat in the pot itself, not on the cooktop. The top of the cooker remains relatively cool. This lowers the risk of burns. In addition, the surface of these stoves is completely sealed to allow for easy cleanup. Another use of the induction heating principle is in the metalworking industry. When a piece of metal, such as a pipe, is inserted inside of an energized coil, the metal pipe is heated. This heating allows for easy bending and shaping. The heat can be controlled to allow for heat treating processes such as annealing. Annealing is a process that adds strength to the metal by slowly and evenly heating a metal to a desired temperature and then systematically cooling it to produce a highly tempered metal. Following on the right side of your screen is a drawing of the Ajax magnetic induction furnace. The furnace is rated at 3600 kilowatts and can easily melt over 10 tons of steel. For the experiments 14-1, the experiment allows you to observe the effects of self-inductance. The materials needed are 1-cylinder shaped magnets, the selection of coils, at least 2 with different numbers of windings, 1 DC power supply, 3 small light bulbs with sockets, and 1 single pole single throw switch and connecting wire. First step is to set up the experiment shown in exhibit 14-1A on your left lower side. Check with your instructor before applying power to the circuit. Step 2 is to close the switch. With the light connected directly to the 6-volt power source, notice that the light burns at full brilliance instantly. Step 3 is to open the switch and connect a coil in series with the light and close the switch, such as the one in exhibit 14-1B, top right. Step 4 is to close the switch. You should now notice a slight delay in the light approaching full brilliance. This delay is caused by the inductance of the coil resisting a change in current. Turn the switch off and insert the iron core into the coil. Once again, close the switch. The light now comes to brilliance rather slowly and never does reach full brilliance. Why does the core increase the delay in the brilliance? Step 7. Move the core in and out of the coil. Note the change in brilliance. How does this relate to self-inductance? Step 8. Finally, repeat the above experiment using a coil with more windings. This should increase the self-inductance. How does this affect your results? And this concludes this chapter questions and experiment for chapter 14 again. Thank you very much.